I will give you back Aaron O'Shea, who will give one of the keynote addresses.
Great. Thanks, Ron. It's a great job setting the stage. Okay, so tonight I'd like to talk to you about our thoughts on the current challenges in scientific publishing and how we might change the system to better serve the interests of scientists. But before I start, I want to make two general points. First, what I'm going to present is not really new. It's not entirely new. Many of you in this room and people listening online have written about, and in some cases even implemented, similar ideas. But what I will do is put these together, I think, in a framework, in a plan that we're excited about and we're excited to get your input about. The second thing I want to tell you about is, in another respect, the ideas I describe are also certainly not entirely my own. They represent the work of Bodo Stern, who is HHMI's Chief Development and Strategy Officer. And he worked in close collaboration with two members of his team, Bojana Conforti and Catherine Brown. All right, so I want to start by taking a step back and reminding us of the purpose of scientific publishing. And I think this is important to do because it really frees us to then think about what kind of system would we design if we were doing it from scratch now to accomplish the objectives of scientific publishing. So publication of research findings does a lot of things, but I think among the most important is to create a public record of original scientific contributions, to give authors intellectual credit for their claims, and to enable others to reuse and to build upon the findings of future research. And I think we now all take this for granted, but back in the 17th century, when the Royal Society started scientific publishing, it was really considered a bold and innovative move to get scientists to reveal their discoveries, their research publicly, in exchange for recognition of their priority claims. So at HHMI, we're, as I mentioned previously, we're really interested in reforming the way we publish research findings. And this is important to us because we invest an enormous amount in research, and we want to make sure that the last step in the process of research, the last step in the research workflow, which is, of course, the sharing of research output, we want this to occur in the best possible way. And so we hope to join with other like-minded organizations and other scientists and use our influence to help catalyze change in scientific publishing to ensure that it serves the needs of science and of scientists. All right, so with that, I want to start by commenting on what we consider to be among the greatest challenges in scientific publishing today. And I should say that this most certainly is not an exhaustive list of the challenges. But from our perspective, these are among the greatest issues of most pressing priority. And among them are things like, for example, publishing contributes to a corrupt incentive system. So we now are in a situation where equating the journal name with quality leads to the tendency to evaluate scientists based on where they publish and not what they publish. And it's particularly alarming now that many early career scientists, and indeed even undergraduates, when I go and visit places, are convinced that they need to have a paper in one of the most prestigious journals in order to move on to the next step in their career or to get a faculty position. So this is a serious problem. Additionally, I think our system has, as is the topic of this meeting, a substantial lack of transparency and accountability. So one reason why the journal name is such a pervasive indicator of quality is because the quality controls that are associated with scientific publishing aren't made available. And we have those controls, but we don't use them. We don't make them freely available. And that means that only the final step, the very act of publication in a journal, serves as a readout of those quality controls. And it just leaves, in the end, the journal name as the proxy of quality. And I think this, too, is a major issue. So our publishing system, I think, wastes resources and time. It takes, on average, 9 months to publish a paper. This is substantially longer than it used to take. Much time and energy and resources are wasted on resubmitting papers after they've been rejected from journals. And much funding is wasted on revisions for publication. Not all of that time and money is wasted. Undoubtedly, papers are indeed improved by peer review and by revisions, but not all of them are. Not all of the input from the peer review process in the current system is beneficial. And finally, and I think this is something to me that's astounding, limited access to research outputs. So for most journals today, scientists can only access research articles by paying fees, subscription fees, online licensing fees, or fees for individual articles. And this clearly limits the access to research, and it limits the ability of scientists to build on published research outputs. And this means it limits the progress of science. And to me, this is astonishing, given that most of our research is funded by the government, by taxpayers who are paying for this work and don't have immediate access to it. So we think these are among the greatest issues in publishing today. And on the next slide, I just want to highlight the steps in the publishing process that contribute to these difficulties. So first, most journals don't make the critiques of the peer reviewers public, all right? And this gives, of course, editors the flexibility to use their own judgment in deciding what to publish without having to account for these peer reviews. But it comes at a great cost, because I think it deprives the rest of us of important critiques that would otherwise help us to evaluate the articles independent of the journal editor's ultimate publishing decision. Second, editor as gatekeeper. So editors determine the fate of publications in our current system. And the problem isn't that editors sometimes make bad decisions, right? There'll always be good and bad editors, whether they're professional or whether they're academic editors. And even good editors will, of course, occasionally make bad decisions, as we all do. But editors, I think, are particularly problematic as gatekeepers because their decision always serves the interest of the journal first and science second. And of course, there's a large overlap in the interests of the journal and science because, after all, the scientists are the customers, they're the consumers. But this overlap isn't perfect, and for some journals, it's less perfect than others. And editors want to publish articles that their customers want to read, like controversial and unexpected findings. And that is not necessarily the same as publishing the best science that's available. All right, and these first 2 points conspire to create the third issue, and that is journal-based metrics. Because the process is non-transparent, the editor's decision to publish is the only visible outcome of the whole evaluation process, right? And that's why the journal name and associated metrics like the impact factor have become such prevalent indicators of quality and impact. And this is a serious problem. It's a serious problem for Hughes, but it's a serious problem for the academic enterprise in general, because it bases the evaluation of scientists on the merit of the journal and not on the merit of the actual contribution that's described in the article. And finally, as I mentioned previously, this paywall issue in the form of fees and subscriptions limits the open sharing of research results. And this limits the progress of science. All right, so how did we get here? And I think it's, when you think about it, quite clear how we got here. The two critical elements of the publishing process, which are the subscription model and editors as gatekeepers, they made a huge amount of sense when print distribution was necessary and was expensive, right? You had to have somebody to select what articles would go into the journal because you couldn't print everything. It was way too expensive. And then when you sent somebody a printed journal, it was totally reasonable to expect payment in return. But these limitations of print don't exist anymore. And there's no meaningful limit on dissemination in our current digital age. It's cheaper and faster and easier than ever before. And so now this gives us the opportunity, as I alluded to before, to imagine what could be the optimal system for disseminating scientific information, question the current process, and to re-envision the roles of editors and reviewers and authors. And I should say, I think there's an additional factor that puts publishing under even more stress and explains why we should act soon. And that is that there's been tremendous rapid growth of the research enterprise in the past few decades. And this has been accompanied by a stagnation in funding. And as a result, there's even more competition for jobs, for funding, and for publication. And this hyper competition just essentially pours oil on the flames and amplifies these problems in publishing. So I think there are ways that we can improve this process and make it much more suited for the digital environment, the process of scientific publishing. And I want to now just walk you through the changes that we envision are one way in which we could replace the problematic steps in the current process that I just described. So one is the topic of this meeting, to make peer review open and publish peer reviewers' critiques with every research article. So the peer reviewers initially might remain anonymous, as is typically the case now. Eventually, I would hope that we would evolve to a system where the names would be revealed, but we can talk more about that. But nonetheless, by publishing the peer reviews, the editor's decision to publish is no longer the only visible outcome of the evaluation process. The published peer reviews provide a second and independent output of this evaluation. So second, shift the decision to publish from the editor to the author. And I think this is one thing that most scientists are perhaps most uncomfortable with, right? But if we do this, the decision to publish no longer serves the interest of a journal, but instead serves the interest of the author. And since authors decide when and what to publish, they will no longer perceive the time and the resources they invest on revisions as wasteful. And I think the big concern that everyone raises when they hear this is, oh, is this really a good idea to put the author in charge? All kinds of bad things could happen. Authors might shamelessly self-promote their own work. But I think in reality, there are several checks on the system that will prevent most people from doing that. So first, every single scientist, even now, cares about their reputation. And that reputation is put on the line every single time each of us publish a paper. All right, so that's one thing. Second, in this new system, the peer reviews are published. And so if the author overrules a peer reviewer who recommends against publication, well, the negative peer review will still be visible to the readers. All right, and the third restraint on the author, I think, is also what we envision as the third change to the process. And that is post-publication evaluation through article-specific tags. So if we want to move away from journal-based indicators of quality that have what I argue is a corrosive effect on academic evaluations, we've got to replace them with better indicators that are first and foremost article-specific, that reflect the quality of the article, and which can capture long-term impact. They can change over time. They can be updated over time. And that's where tags come in. The idea is that tags are shorthand measures of a particular quality feature of research articles. And you can imagine many different quality features. For example, tags could display scores for technical quality, for reproducibility, for the number of citations, and we could go on and on. And I won't say more about this because Bodo Stern will give a short presentation on this idea of tags tomorrow, and will provide a lot more detail. And finally, open access. I think we feel very strongly that all primary research articles need to be made freely available at the time of publication so that every researcher has an opportunity to build upon this research and science moves at the fastest speed possible. All right, so this slide summarizes the status quo and the proposed future state. So on the left are the challenges that I introduced in the very beginning of this talk. Next to it are the processes that contribute to these challenges. In the middle right are the 4 proposed changes that I just talked about that lead to the benefits on the right. So opening up peer review will, of course, make peer evaluations accessible to everyone. It'll make peer review undoubtedly more constructive and will enable us eventually, I hope, to recognize scientists for good peer reviews. Specifically, if eventually peer reviewers sign their reviews and we treat peer review for what it really is, which is scholarly activity. It's a substantial amount of the way many of us spend our time. Then we can reward and recognize scientists for good peer reviewing. Scientists could add peer review activity to their CV. Peer reviews could be cited if they make contributions to science. And scientists, in turn, if this change were adopted, could take peer review even more seriously and do their best job possible. So shifting the decision to publish from editors to authors will get rid of all the time and resources that are wasted on unnecessary revisions and eliminating time that we waste reformatting and resubmitting papers to another journal upon rejection. This step will indirectly also improve peer review since the peer reviewers will no longer have what I think in many cases is now a conflicting role in advising both the author and the editor. They're advising the editor about the impact of the work and the suitability for the journal. But in reality, peer review is best suited to focus on advising the author on improving the work, on improving the manuscript, just as most of us ask when we ask of a colleague to comment critically on our work. Peer review should be constructive and critical. Creating article-specific metrics in the form of tags we talked about hopefully will shift the incentive system away from this journal-based metrics, and ultimately we hope scientists won't feel the need to publish in highly selective journals. And finally, open access I talked about, we hope will increase sharing and reuse of research findings. So the real issue is, this is sort of the utopia, or one utopia, at least in our view, and the issue is how can we implement this revised process? And clearly this is the major challenge, and I think one piece of good news is that these 4 changes, although they're highly synergistic, could be implemented separately. For example, peer review changes that are the topic of this meeting. And we hope journals will start to experiment with these proposed changes. So finally, what do we want and expect scientific publishing to look like? I wrote here in 10 years, but I hope it's sooner than 10 years. And so I think the implication of author-driven, peer-improved, and open access publications is that editors and journals will be less relevant for the publishing of primary research. We expect that the number of journals will shrink, and I think that's not a bad thing. It's not clear we need 28,000 scholarly journals in this digital age to disseminate primary research. In the future, we could have a few big publishing platforms where we collect primary research articles, peer reviews, comments, and the types of tags that I briefly described. But I want to emphasize, this doesn't mean that journals and editors aren't important in our model. I think they will play an absolutely critical role as curators of the literature. The literature is larger than ever and will get even larger. And together with the scientific community, we hope journals and editors will develop what is currently a really underserved area of publishing, post-publication evaluation, including the tags I mentioned, but there might be other models of post-publication evaluation. I also think there's some money to be made here. We feel very strongly that a subscription model is not okay for the publishing of primary research articles, but we don't see anything wrong with charging fees for curation services. Okay, and so finally, I just want to end here by saying that I think I'm sure you're all aware, there are major challenges with changing the publishing system from its current state to some state akin to what I described. There are large financial issues and technological issues to be overcome, but I think the biggest one here is number 2, the cultural hurdles. What do we need to do to get scientists and institutions to adopt and reward new publishing practices? And so I want to stop there, but I want to emphasize that we'd be delighted to hear any comments, any feedback, any other ideas you have on the thoughts I presented today. Thank you.
Well, I'm sure there was about 4 hours of questions for Aaron. But I think what we're going to do is hear all of the keynote talks first, and then there's going to be a discussion with all 3 speakers. So very pleased to have Jeremy Berg here today, and in his role as Editor-in-Chief of Science, and also a wonderful member of our scientific community. So Jeremy.
Well, thanks very much. It's hard to follow such a thought-provoking and sort of forward-looking talk. Ron's comments reminded me of actually my first, not my first submission, but my first review I got as a graduate student, which certainly highlights the importance of openness. And I swear I'm not making this up. The first line of the first review I got was, "The authors are obviously unfamiliar with our unpublished work." Fortunately, the editor was sympathetic that this wasn't really our fault. But in a different world, that could actually be a legitimate criticism, I suppose. So I also want to, this is also deja vu, partly because of the ASAP Bio meeting a couple of years ago, but also when I was at NIH, I was involved in one of the big evaluations of the NIH peer review system, and all of these issues are slightly changed, but are similar to things that we discussed, and I'm sure NIH is still struggling with a lot of the same issues. So let me see, to go forward here. Is it the mouse? Or just, oh, here.
Yeah. No, it's this thing.
Yeah.
You want to get to the next slide?
Yeah, thanks. Okay. So I just want to frame, my sense of this meeting a little bit from some of the perspectives that I just highlighted before. So, there are multiple audiences, and Aaron touched on this a little bit for peer review now. And I think they do serve different roles, and, some of the things that we're discussing in terms of more openness will have implications for the different aspects of publication. So, from an editor's perspective, they're really looking for three basic areas of input from peer reviewers. One is, as was mentioned, the potential importance of the findings. And, this depends on the journal and the context, and editors do depend on input from experts in the field to sort of say, how big a deal is this? Is this something that's really, changing people's perspectives and so on? Again, this was something that NIH certainly has struggled with and still struggles with is how to judge potential impact, the importance of the problem and so on, in addition to the more technical aspects of the proposal. And then technical analysis and so on is also very important. And then there's also some role for identification of other issues, and that's intentionally a very broad and vague category, but peer reviewers point out other issues that may have come up with misconduct or other irregularities or the various things that journals, good journals anyway, spend a lot of time checking about, data availability and things that support reproducibility and all the sorts of things which I think the scientific community has been understandably trying to push for. And those come up and are highlighted in ways that are important to the overall process. Now, the authors are obviously a key audience, and the evaluation of the manuscripts that they've submitted are useful for two ways. First off, it's a key part of the decision about whether a paper is going to be published in a particular journal, but also feedback and improving the science, and both for if the paper does get rejected for resubmission or get revised, gets resubmitted to the same journal, gets revised and submitted to a different journal, or just general feedback from thoughtful critics about their research that can guide future research directions. I've certainly, over my scientific career, have gotten comments on papers which are, initially annoying, and then become, the more you think about them, you realize that they have a good point, and they get factored into, thinking about where to take projects in the future. One of the themes for the meeting is other potential audiences. So certainly one other audience are other reviewers, and some journals certainly have already moved in a way in this direction in a big way. Science has for a couple of years now used a cross-review system where at the end of the peer review process, comments are shared between the reviewers, and they're allowed to react to each other's comments. And this is, the response rate is modest. Not everybody responds, but there are certainly some people who engage pretty heavily. And the lack of response doesn't necessarily mean that reviewers aren't reading it and responding. They just think that they're pretty well aligned. Sometimes there's some short but important discussions that one reviewer will comment that somebody made good points that have changed their comments a little bit, or in other cases, there are disagreements that help the editors sort through often contradictory reviews. That's another aspect of peer review, which I think is really important to keep in mind, is that these are not, very few reviews are nice, crisp, clean, black and white, this is a great paper and it should be published, or this is, has a lot of flaws and shouldn't be published. There's a lot of room in the middle for this part is good and the other part isn't, or there's a conceptual problem, but the experiments look okay, or the interpretation is wrong, and so on. And figuring out how to sort all of that out in any system is important. And then, again, open peer review where peer reviews are shared. The concern, I'll talk on this in a second, is, which I think is something we do have to keep in mind, how much will that distort what people write? And I don't pretend to know the answer, but I think people write differently depending on who they think the audience is. Certainly in the case of non-anonymous peer review, if you're writing and you know that your colleagues are going to know that you reviewed their paper, that's going to change how you approach the problem, whether you'll be less critical or more critical or differently critical or whatever else. I think it's just something to keep in mind. So finally, just to close my remarks, I think, some of this are sort of general questions about policy development. So the question of can peer review be improved, we need to know, improved in what way and where are we now? And I was thrilled to see on Twitter earlier that on the ASAP Bio, there are a couple of recent surveys and so on looking at some aspects of satisfaction with various aspects of peer review. I think it's important to really think hard about what we're trying to achieve in terms of improving peer review. Is it better advice to scientists? Is it better information for editors or other curators about the papers? And those sorts of areas, I think need to be thought through. The other key question, and this was certainly one of the biggest topics of discussion in the NIH peer review, is how can participation of appropriate reviewers be encouraged and achieved? In any case, getting the right people to engage on peer review is a big factor in addressing quality. And again, it's not so simple with, particularly with modern science, with lots of different disciplinary aspects represented in a paper. You need to have not only experts in the biological area, but you may need statistical expertise and other sorts of people who can look at different aspects of the experiment and provide good criticism of the technical aspects or conceptual aspects of different parts of the paper. And then to close, and I think this is one place where I think Erin and I agree completely, which is culture, culture, culture. And a lot of this comes from incentives. Improved assessment of scientific contributions without flawed surrogates. That means, why in the world would anybody judge papers on where they're published? The impact factor is one of the great mysteries of my life, is how impact factor sort of has taken on such a big role when it's such a flawed metric. I think it's convenient, and institutions are remarkably lazy about assessing the most important things that they do. And I find this sort of astounding that institutions will rely on number-driven, very automatic assessment of whether or not to give a scientist tenure, rather than reading the papers or talking experts in the field and deciding did they do anything important. I have been fortunate over my career and have published some papers in high-profile journals, some of which have been really important and some of which have been really not very important. It was hard to judge at the time. There are other papers that we published that have been in new journals or in journals that weren't, particularly high profile. So I'm certainly all in favor of pushing the scientific community and academic institutions to be thoughtful about how to make these sorts of assessments and move away from impact factor and other parameters that have really distorted things and corrupted things, I think, in really unhelpful ways, and have led, to this you know, in some ways to this emphasis on you have to publish in a small number of journals in order to have a viable career, which is just is nonsensical and frustrating and so on. And, you know, I don't think that the Science, Nature, and Cell journals have been very much responsible for it. It's really been the scientific community collectively that has made this so important. And then the last point is meaningful incorporation of desired community activities such as peer review and academic assessment. Again, this is something that I think is really important, but the word meaningful is really meaningful in this context. I mean, I think universities have struggled with assessment of teaching for promotions for decades, many decades. And, you know, I think in many cases, even though now there are lots of student evaluations and various factors that get built into it, the number of faculty who have really improved their promotion chances by being excellent teachers is still pretty small. And in fact, there are examples the other direction where, you know, being a good teacher is a sign that you're not spending enough time writing grant proposals and things that are going to, you know, bring money into the institution. So I think it is important to develop the metrics, but also to work on the culture and really get buy-in in the deepest possible way from the institutions, that if they're going to talk the talk about this, they need to walk the walk and really make it important. You know, in the past, it's, you know, early on in my career, and, you know, maybe this is just my perspectives as a younger faculty member and so on, there was a strong cultural expectation that, you know, reviewing papers and doing a good job and teaching and doing a good job was just an expectation. It was part of your job, and people did it because there was a lot of subtle peer pressure that this was just what was expected of you. Now, I think with so many other pressures, that gets lost and to some degree with other metrics being put in place. So there need to be ways to build this up. There are some communities where this is done, and there may be places to look to, for example. So in some medical areas where continuing medical education credit, there are systems where reviewers who would do a good job as judged by editors rather get CME credit for doing a good job, both volume but also quality. In basic science, there isn't the same accreditation, you know, system or need and so on. So that's not directly applicable, but it'd be interesting to look to see whether that does have an effect and whether people think it matters or not, just to see whether there's some examples. So we'll stop there. I'm really looking forward to the meeting. I think these are really important questions. I haven't addressed the sort of open access, so on. I think we do have to keep in mind that there are many aspects of publication, even with the internet and so on, that really do cost money. You know, copy editing and checking all the, you know, in addition to the editorial processes, managing the system, copy editing, checking all the sorts of things that enhance reproducibility and so on. And those costs are real, and the money has to come from somewhere. You know, to some degree, that the different models are different accounting systems, but getting the costs out of the system is going to be, not as simple as snapping your fingers with a different model. So I'll stop there, and again, be glad to participate in discussions later on.
Great, thank you, Jeremy. And now I'd like to hear from Mike Lauer, who is the Deputy Director of Extramural Research at the NIH.
Thanks, Ron. Okay, good evening, everybody. Good evening. Okay. All right, so this is a map of the United States. It's broken up into 3,000 plus counties, and it shows the results of the 2016 presidential election. The red counties voted primarily Republican, the blue counties voted primarily Democratic. So here's a question. A study of the incidence of kidney cancer in the 3,141 counties of the United States shows something rather remarkable. The counties in which the incidence of kidney cancer are lowest, or is lowest, are mostly rural, sparsely populated, and located in traditionally red states. What do you make of this? Okay, so I have shown this to a number of audiences, in some cases very senior scientists, in some cases junior scientists, and I get a variety of answers. The answers go something like this. The air is cleaner, the water is cleaner, the diet is better. Some cases it's more negative, like there's no access to medical care, so the kidney cancer doesn't get diagnosed. People are dropping dead of something else, so they don't get a chance to get kidney cancer. We call that competing risks. But those are the kinds of answers I typically get. All right, now, here's another way of looking at these data. So same data. This is a map of the United States. The green or the teal counties, those are the counties in which the incidence of kidney cancer is lowest. And the orange counties, those are the counties in which the incidence of kidney cancer is highest. And you'll notice that the counties in which the incidence of kidney cancer is highest are rural, sparsely populated, and primarily located in red states. And you may say, well, that's because they have, there's more pollution, or there's a lousy diet, or there's less access to medical care. But you'll notice that many of these counties are right next to each other. So, you can't have it both ways. You can't say that it's the highest and it's the lowest. So, what's going on? So I'm going to show you another way of looking at the exact same data. Now, the x-axis here shows the population of the county. So this is from 1,000, 10,000, 100,000, and a million and so forth. And the y-axis shows the age-adjusted rate of kidney cancer. Each dot is a county. And you can think about, and if you look at this, what you'll notice is that the counties that have low populations have an extreme degree of variance. So some of these counties have very high rates of kidney cancer, and some of the counties have no kidney cancer. The incidence is zero. So if you don't want to get kidney cancer, you know where to go. And then as you'll notice that as the population of the counties goes up, we are converging on a certain rate, and the degree of variability is much less. Okay, so now why am I showing you this? Imagine that these aren't counties in which we're trying to measure the incidence of kidney cancer. These are scientific studies. In this case, the scientific studies, these are 3,000 scientific studies that are trying to answer a question, what is the incidence of kidney cancer? But it could be 3,000 scientific studies that ask any question. And those scientific studies that have a relatively small amount of information, where the information is sparse, and the information is usually sparse because the sample size is low, there's going to be a huge amount of variability. And some of them invariably are going to show some extreme results. And those extreme results will be really exciting. And they'll get sent into a journal. And the peer reviewers will think this is great. And it will get published, and it will cause a great deal of excitement. And then later on, somebody else is going to attempt to reproduce that scientific study. And invariably, they're going to get a result that is a lot less exciting. Even if they're working with smaller sample sizes, they're going to, just by regression of the mean, they're going to be closer to the middle. And if they do a larger study, then they're almost certainly going to get a more robust answer, which is a lot less exciting. And we see this in science all the time. This is a very common phenomenon. Now, I remember, I'm a cardiologist, and I remember when I was in training early on, we were so excited about intravenous magnesium. Intravenous magnesium reduced the rate of death from heart attack by 50%. That's what the small trials were indicating. Nothing reduces the incidence of anything by 50%. I mean, that alone should make you not believe it. And then later on, when the large study was done, it was found that actually, if anything, intravenous magnesium was slightly harmful. All right. So this phenomenon whereby we get all excited about what we see in small samples was described by Daniel Kahneman. Daniel Kahneman won the Nobel Prize in Economics in 2002. He's actually a psychologist, and he and Amos Tversky did groundbreaking work on how people think and how the way we think often leads us to incorrect conclusions. And he says, this is the law of small numbers. Large samples are more precise than small samples. Large samples are more precise than small samples. I think we all get that. Okay, here's the hard part. This means that small samples yield extreme results more often than large samples. Okay, and that's exactly what we saw here. The small samples are much more likely to yield the extreme results. The exaggerated faith in small samples is only one example of a more general illusion, a view of the world that is simpler than the data justify. Now, I certainly remember when I was a practicing cardiologist, and I would hear over and over again from patients comments like, I am not going to get a flu shot because my neighbor got a flu shot and she got the flu. Or I am not going to take statins because my neighbor took statins and her muscles got sore, and therefore I'm not going to do it. And that's based on a sample size of 1, but based on that, we make sweeping conclusions. All right, so now let's shift gears a little bit. This problem of sparse information in scientific studies is endemic. This is a beautiful paper. I'm just curious how many of you may have read this? Few of you have read this. For those of you who have not read it, let's call it required reading. So this is called Power Failure, Why Small Sample Size Undermines the Reliability of Neuroscience. I just cross out the word neuro. There's nothing special about neuroscience here. This is true for all science. The authors here, Catherine Button was the lead author, and she says here that a study with low statistical power has a reduced chance of detecting a true effect. I think that's something that many of us get. We know that. But it is less well appreciated that low power reduces the likelihood that a significant result reflects a true effect. The real question in any kind of scientific report is this true? Is this something which I can really believe? And what is grossly underappreciated is that a small sample size study is more likely than not to give you a result that is simply not true. And this is particularly true if we're early on in the march of science where the preliminary data, what we might call a Bayesian prior, is relatively low. And there the risk is exceedingly high. Now, they go on to say the average statistical power of studies in neuroscience is very low. The consequence of this includes overestimates of effect size and low reproducibility of results. So here's an example. They looked at a number of animal studies. These are rodent studies that where they were doing water maze and radial maze experiments. And they calculated that in order to get an adequate power, an 80% power or 90% power, you needed hundreds of animals in each study. And the mean or the median number of animals in the study were more like 20. And this is very typical. Studies are grossly underpowered. They say here is what is particularly striking is the inefficiency of a continued reliance on small sample sizes. This has an ethical dimension. Unreliable research is inefficient and wasteful, and this is true for both human and animal research. Why would one do an underpowered study? If the study is negative, you're not going to believe it because the study wasn't powered to detect the true effect if it's really there. And if the study is positive, you shouldn't believe it because it's more likely than not that the result is a false discovery. So why do you do it? Okay, so now switching to NIH, a number of years ago, colleagues in NINDS, this was primarily led by Shai Silberberg, and Story Landis wrote this paper, A Call for Transparent Reporting to Optimize the Predictive Value of Preclinical Research. And they say here that at a minimum, so they're talking about what is it that should appear in the report, in the published report. At a minimum, studies should report on sample size estimation, whether and how animals were randomized, whether investigators were blind to the treatment, and the handling of the data. Now, the reporting of sample size estimation, of course, assumes something. It assumes that the sample size was actually estimated. And it not only assumes that, but it assumes that the estimation took place before the experiment was done and not after a peer reviewer happened to pick it up and say, how did you come up with your sample size estimation? All right, so how are we doing? So this is from a different set of literature. This is from Cardiovascular Science. This is a paper that was published in Circulation Research just a couple of months ago. And they were looking at how high quality were the reports in basic cardiovascular science. So here they looked at a number of studies involving different animal models. There were about 3,300 papers or so that they looked at here. And the question was, how often did the authors mention randomization in their report? And you can see here that it's about maybe 30%. It's not zero, but it's not particularly good. And for mouse studies, which of course are the ones that are done most commonly, it was only about 15%. By the way, for blinding, the results were similar. Now here's sample size estimation. What percentage of these reports said anything about sample size estimation? And it's essentially zero. It's maybe about 1 or 2%. A very tiny, tiny number. Now, why am I showing you this? Because peer review is not going to help. If 98 to 99% of your peers are paying no attention to sample size estimation, then it doesn't matter how transparent the peer review is, we're not going to be able to solve this problem. So how are we going to do this? Is peer review, as currently practiced, is unlikely to help. So a number of funders have become worried about this. I will say that NIH is worried about this. This was an interesting paper that appeared in Nature a few years ago about funders in the UK who are starting to demand strong statistics from animal studies and starting to really worry that they're spending huge amounts of money on highly underpowered experiments that are highly likely to lead to irreproducible results. Now, why is this happening? Why is it that sample size estimation is not happening or that it's avoided? So I found this is a terrific paper, and some of the slides I showed you before is actually taken from it. It's written by Howard Weiner. Howard Weiner is a statistician at the Wharton School at the University of Pennsylvania. He's also a member of the National Board of Medical Examiners, and he wrote this article called The Most Dangerous Equation. So equations can be dangerous either because we know about them or because we don't know about them. Yeah, E equals mc squared is an example of a dangerous equation, which is dangerous because we know about it. And then he presents another equation. And, you know, so I have a background in statistics, and some of my mentors have told me, never, ever, ever, ever show a mathematical equation in a talk. Because if you do that, you will put your audience to sleep. But I'm pretty late in the talk now, so I think that I'm going to go ahead and do it. I'm going to take the risk, and I'm going to show you this equation. That's the equation. I'm just curious, how many of you know this one? Okay, a few of you, so congratulations. What's it called? What is this equation called? Anyone? What? Yeah, standard error of the mean, but you know who invented this? So this equation is called De Moivre's equation, Abraham De Moivre. He was a mathematician in the early 1700s. This equation was published in 1730. So it's the standard error of the mean is equal to the standard error divided by the square root of the sample size. So it's inverse to the square root of the sample size. Now the square root's really important because that means that if you increase the sample size, you don't increase the amount of information by a proportional amount. You only increase it by the square root, which means that to get a robust study, you need a really large sample size. And what's the problem with that? Getting a really large sample size is hard, and it costs a lot of money. And I'm sure that some of you will ask me about that in the discussion, so we can talk about that at the time. But, so he goes on to say that ignorance of this equation has led to billions of dollars of loss over centuries, yielding untold hardship. And I would say that that's an underestimate. It's probably hundreds of billions or trillions of dollars. It is no revelation that humans don't fully comprehend the effect that variation has on the phenomena that they see. That's something that Daniel Kahneman talked about. So the question is, who's going to fix this? Who is going to bring this? If you think about this, this is one of the most fundamental aspects of experimental design, which is how much information are you going to collect during your experiment? Who's going to fix this? The scientists, and so far we haven't done very well, editors, reviewers, statisticians, the reviewers that we pick, so we can talk about that. NIH is very concerned about the reproducibility crisis. This article Francis and Larry wrote a few years ago, and we've taken a number of steps to try to improve the rigor of the proposals that we see in our applications. We are very pleased to see that journals are stepping up to the plate. Journals have been very actively involved in this process, and I think a key part to thinking about scientific rigor and transparency, and as is clear by this conference and how this conference is assembled, is that this is a multi-stakeholder problem. We all have this problem, and this is not going to be something that any one party is going to fix by pushing a button. So this is an interesting number of journals are doing this. By the way, I'm a clinical researcher, and checklists for clinical research papers and for clinical trials is nothing new. This is something that a number of journals have been doing for a long time to improve the quality of the reporting of the articles that they see. All right, so new reporting standards for nature journals are intended to improve transparency and reproducibility. So I'm going to show you, this is an actual one that I pulled down from the web. This is I'm not picking on neuroscientists. I don't know, this thing just randomly came up. So this is Nature Neuroscience. This is the reporting checklist for the Nature journals, and they have a section there called Statistics and General Methods. And they ask a question: is there a justification of the sample size? And then assuming that they might know what the answer is, they say, even if no sample size calculation was performed, the author should report why the sample size is adequate to measure their effect size. And this was from an actual checklist that I found. We chose the sample size based on literatures in the field. And you see this a lot. And you really wonder, okay, was there a statistical reviewer? I'm going to guess probably not, because if there was a statistical reviewer, they would say, well, this experiment was not properly designed. The sample size was not thought through before the experiment was done. This is almost certainly a woefully underpowered study, which means there's a high likelihood that this is a false discovery, and we can just stop there. All right. So let me end some closing thoughts here. So who's in charge? You know, we have a serious reproducibility epidemic, or endemic. Maybe I should use the word endemic. It does not help any of us in science, in funding, in publishing, to be putting out a whole lot of woefully underpowered studies that many of which are going to be wrong. So we have to deal with this. In this day and age, can we justify publishing papers that focus on populations of humans or populations of animals without statistical review? There are some journals, so I've published, for example, in New England in JAMA and Annals of Internal Medicine. And the way it works there is that the articles are the manuscripts are first reviewed by content experts. And if the content experts say this is potentially interesting, then it's given to a statistical reviewer. And some of these journals actually have full-time statistical reviewers in-house. And then the statistical reviewers go through these papers with a fine-tooth comb, and only then the editors make a decision about whether or not they want to pursue it. We must ask ourselves whether or not in this day and age, where data is so important and where the opportunity to make mistakes with data are so high, we should be allowing anything to go through without statistical review. All right. Will transparent peer review clarify statistical quality? So I had an experience, some of you may know about this. I wrote a peer review on a study of cell phones in mice, gnomes, and rats, cell phones in rats. And it wasn't meant to become public, but it did become public. And the result of which was that I spent an entire Friday afternoon talking to a whole lot of journalists. But in my review, I said, I don't believe these results because this is a woefully underpowered study and this is almost certainly a false discovery. The authors of the paper themselves admitted that the power of the study was 10%. And that was a very transparent review. And I have to say, in retrospect, it wasn't planned that way deliberately to begin with. But I have to say, in retrospect, this was probably a good thing. And Aaron, this gets exactly to what you were talking about. The peer review actually is what attracted more press attention than the article itself. And what about post-publication statistical review? And one can imagine that if we're in an era where data is being freely shared, and people can download the data and do their own statistical analyses and say, well, here's what I did. I'll end with one last story. John will remember this. There was a paper that was undergoing peer review, and it was put on a preprint server. And the authors not only put on the preprint server their paper, but they actually put the data there. And John sent me an email one day and said, you got to look at this. So anyway, I downloaded the data. The data were there, and had a fun afternoon analyzing it. Analyzed it in a very different way from the way the authors did. And then John and I sent an email back saying, we found your paper very interesting. And by the way, here's how we analyze the data. Here's the code. Here are the results. And the authors wrote back saying, oh my God, this is terrible. You must promise not to publish what you've done. I haven't even published my paper yet, and other people are analyzing my data. And we said, don't worry, you have nothing to worry about. We got an acknowledgement there, and actually, I think it changed the paper. They actually paid attention to what we had done, and they changed the tone a little bit of their paper. Actually, they changed the tone a lot of their paper based on the experience that we had. So that was a kind of a, you might call it post-publication statistical review, but maybe that's another thing we can talk about. Thank you. Sitting here.